The transition from abstract physics to a functional digital model is best understood through the lenses of two distinct perspectives: the conceptual progression of the project and its real-time operational logic. The conceptual journey. The state diagram. The state diagram outlines the evolution of the project, starting with the foundational principles established in the derivation sheet. This journey begins with a rigorous mathematical proof showing that when a vector's movement is governed by a cross-product relationship with a fixed axis, two specific physical properties remain unchanged: the length of the vector and its angular relationship with that axis. From this proof, the narrative moves to the derivation of the angular frequency, identifying that the speed of the vector's rotation is determined entirely by the strength of the fixed axis. This theoretical groundwork acts as the bridge to the practical demos. The first demo focuses on interactivity, allowing users to manipulate the environment and see real-time verification of those constant physical properties. The second demo focuses on computational dynamics, using a step-by-step numerical method to verify that the vector traces a perfect conical path as predicted by the theory. The operational logic. The sequence diagram. While the state diagram shows how the project was built, the sequence diagram illustrates how the simulation actually functions during a live session. This flow is divided into three distinct phases that mirror the core concepts of the derivation sheet. The initialization phase. Everything starts with the user. By adjusting sliders to set the initial position and size of the angular momentum vector, the user defines the starting state. This corresponds to the initial conditions mentioned in the derivation of the motion. The physics and verification loop. Once the simulation begins, the engine takes over. It uses a numerical integration method to calculate how the vector should move at every tiny interval of time. Crucially, as the engine moves the vector, it performs a continuous checkup to ensure the vector's magnitude and its projection onto the fixed axis have not changed. This live verification provides immediate visual proof of the conservation laws derived in the initial problem set. The rendering phase. Finally, the data is handed off to a visualizer. The engine updates the position of the blue vector and extends a yellow traceline to show the path already traveled. This creates the conical visualization that confirms the pure rotation described in the takeaways of the derivation. Together, these two diagrams transform the static proofs of the derivation sheet into a dynamic narrative of movement and conservation, showing that the vector is continuously pushed in a direction perpendicular to both itself and its axis, resulting in a steady, predictable precession.